Welcome to the cosmos, where time bends and the universe reveals its most mind-bending secrets. Today, we're diving into one of the most fascinating aspects of Albert Einstein's general theory of relativity, time dilation. Prepare to stretch your understanding of time itself. Imagine you're aboard a spaceship traveling at speeds close to that of light. Back on Earth, your family celebrates birthdays, seasons change, but for you, time seems to crawl. This phenomenon, where time runs slower the faster you move, is known as time dilation. Albert Einstein, with his general theory of relativity in 1915, showed us that what we perceive as the force of gravity, in fact, arises from the curvature of space and time. Einstein proposed that time is not constant and can be affected by speed and gravity. This was a radical departure from the Newtonian view of a universal, ticking clock. Time dilation occurs in two key scenarios: velocity time dilation and gravitational time dilation. Velocity time dilation happens when an object moves at significant fractions of the speed of light. Gravitational time dilation, on the other hand, is the effect of gravity on time. Massive objects like planets and stars warp the fabric of space-time, causing time to slow down near them. The closer you are to a massive object, or the stronger the gravitational pull, the slower time moves. This is why time on Earth moves slightly slower than for satellites in orbit. You might wonder, is this just theoretical? Not at all. GPS technology relies on correcting the time dilation effects. Satellites orbiting Earth experience less gravitational pull but move faster, leading to both types of time dilation affecting their clocks. Engineers must account for these differences to ensure the accuracy of GPS positioning. Without adjustments, GPS systems would be off by kilometers. Experiments have confirmed time dilation too. The Halfel-Keating experiment in 1971 flew atomic clocks around the world in airplanes, showing time did indeed slow down for the moving clocks, just as general relativity predicted. The implications of time dilation are profound, especially for future space travel. Astronauts traveling at high speeds to distant stars could experience time much more slowly than people on Earth, a scenario often explored in science fiction. For deep space explorers, this could mean returning to an Earth that has aged decades, or even centuries, while they've aged only a few years. Time dilation challenges our very perception of reality. It suggests that time, something we consider constant and unchanging, is fluid and can stretch or compress. This has profound philosophical implications about our place in the universe and the nature of time itself. It reminds us that our everyday experience is just a tiny slice of the universe's vast complexity. What we take for granted is fixed, like the flow of time, turns out to be deeply intertwined with the fabric of space and the distribution of mass and energy throughout the cosmos. As we've journeyed through the concept of time dilation, we've seen how it's not just a curious footnote in physics, but a fundamental aspect of our universe. From the GPS systems guiding us on Earth to the potential future of interstellar travel, the effects of time dilation weave through the fabric of our daily lives and the universe itself. Time dilation invites us to ponder deeper questions about the nature of time, space, and our place within this grand cosmic tapestry. It challenges us to rethink our perceptions and opens up new vistas of understanding about the universe and our role in it. Thank you for joining us on this voyage through time and space. Remember, the universe is not just stranger than we imagine, it's stranger than we can imagine. Until next time, keep looking up and questioning more.